The first derivative test helps to determine whether a critical point of a function is a relative maximum or a relative minimum. This lists out the procedures for doing the first derivative test. 1. Find the first derivative of the function. 2. Set the derivative equal to 0 and solve for values of x that satisfy f prime of x equals 0. These are called the critical values. Values that make f prime of x undefined are also called critical values. Step 3. Substitute the critical values into the original function to find the critical points. Step 4. Evaluate f prime of x at a value of x to the left and 1 to the right of each critical point to develop a sign diagram or a sign chart. Step 5. Use the information from the sign diagram or sign chart and selected points to sketch the graph. Let's put the first derivative test to use. Example 3 says use the first derivative test to help graph the function f of x is equal to x cubed plus 6x squared plus 9x. So if we want to use the first derivative test, then the first thing we want to do is find the first derivative of our function. So using the power rule, we'd get 3x squared plus 12x plus 9. Step 2 says to set the derivative equal to 0 and then solve for x. So we get 3x squared plus 12x plus 9 is equal to 0. Note that I can factor out a 3 from each of those terms. And we would get that. And now we are trying to solve for x. So that can factor into x plus 3 and times x plus 1 is equal to 0. And then if we're solving for x, we can divide both sides by 3. And then from here, we can set x plus 3 equal to 0 and x plus 1 equal to 0. If we solve both of those equations, we would get x equals negative 3 and x equals negative 1. So these are our critical values. Step 3 in the first derivative test says to take these values and plug them back into our original function to get the critical points. So I'm going to evaluate f of negative 3, which is negative 3 cubed plus 6 times negative 3 squared plus 9 times negative 3. That's negative 27 plus 6 times 9 is 54 and minus 27. And that is equal to 0. Then we want to evaluate f of negative 1. That's going to be negative 1 cubed plus 6 times negative 1 squared plus 9 times negative 1. And that is going to equal negative 4. This means that our critical points are going to be negative 3, 0, and negative 1, negative 4. And the next thing that we want to do is we want to make a sign chart or a sign diagram. And the way that we do that is we kind of create and think of that as an x-axis. And here I'm going to plop in negative 3. And here I'm going to plop in negative 1. And we kind of want to figure out what's happening in each section of those intervals. So I'm going to separate them with a little dashed or dotted line here. And so again, don't forget negative 3 and negative 1 are our critical values. And I tend to call these things that I'm going to fill in test numbers. So now here in this interval, we want to choose what I call a test number, and that's any number between negative infinity and negative 3. And usually it's easier to go with integers if possible. So I'm going to choose negative 4 as a test number. Then in -3 and -1, in that interval, I want to choose a number between those. I'm going to choose -2, and then I am going to choose a number between -1 and infinity, and there I'm going to choose 0. And here I'm going to put f prime to indicate I want to plug those test numbers into our first derivative. So let's go ahead and do that for -4. So I'm going to evaluate f prime of -4. And if we do that, that's going to be 3 times -4 squared plus 12 times -4 plus 9. Now, it turns out that we don't even really need to simplify the number if we don't want to. We just need to figure out whether f prime of -4 is positive or negative for the purposes of this like curve sketching. But let's see, -4 squared is 16, so we have 3 times 16 minus 48 plus 9. And 3 times 16 is 48 minus 48 plus 9. So that should be an 8. So we get 0 plus 9, so this ends up equaling 9. So I'm just going to put a plus sign here to indicate that our number is positive, which tells us that on this interval, our function is increasing. And then let's plug in f prime of -2. Which is going to equal 3 times -2 squared plus 12 times -2 plus 9. That's 3 times 4 minus 24 plus 9. That's 12 minus 24 plus 9, which is just going to be a negative number. So I'm going to put negative right here. And then last one, f prime of 0. You'll see that the first two terms would disappear, and it ends up being 9, which is positive. So that means that our function is going from increasing to decreasing to increasing again. I'm going to go ahead and erase this stuff on the side here. What does this sign chart tell us? Well, it tells us a few things. It tells us what's increasing and decreasing. And it also tells us that at -3, if it's increasing and then decreasing, we have a relative max here. And then if it goes from decreasing to increasing at -1, we have a relative minimum here. So let's draw our y-axis and our x-axis. And here is -3, and here is -1. And we know that our graph goes through the point -3, 0, and -1, -4. So those are our relative max and min. And each of these terms has an x in it. So if I plugged in f of 0, all of those terms are going to turn into 0 and we get 0. So there's an x-intercept here. And so we have like the general shape of our function. So we know it's increasing. There's a relative maximum there, a relative minimum there, and then it goes back to increasing. And so our graph is going to look something like that, just a little bit better looking than how I can draw it. Let's go ahead and verify that on Desmos really quickly. So I have y equals x cubed plus 6x squared plus 9x. And so see, it looks like that, just a lot better looking than how I could draw it. So there are our values, either our x-intercepts or our relative max and relative min. So that was what we wanted to look for as far as sketching that graph.